Good afternoon, everybody. I'm going to talk about diversity in machine learning, and this is really going to be two talks in one. So I'll sort of shift gears halfway through. So two talks for the price of one. The first one is going to be on algorithmic diversity, and this one is going to be a little bit technical. And what I want to try and accomplish in this first part of the talk is to help people understand. We saw some great talks from Stephanie, from Scott, from many other people that are talking about the concrete advantages of diversity when it comes to decision making. And so in the context of machine learning, I want to try and understand why that might be the case, just so that people can understand a little bit of the mechanisms whereby diversity can improve an algorithm. And then after that, I want to shift to a different but also very important topic, which is once we have these algorithms, to what extent does the bias in these algorithms impact human diversity? So they're both very important topics. Okay, so let's jump in with algorithmic diversity. So the motivating question again is, how does diversity improve the performance concretely of a machine learning algorithm? So that's the question that I want to try and get to. So we're going to start with movies. So you guys are going to learn a lot about the movies that I like and don't like in the course of this talk. You can ask me any questions except about movies because my opinions are correct on that. And so there's no need for any debate. So I want to build a classifier that's going to tell me what movies I might want to watch next. And so the way a classifier works is that you take a training set where I have a bunch of data that I know the answer, do I like it or not, and I want to build a tool that's going to predict whether I'm going to like something else. So that's what I just said. So you use a training set to build a classifier that can make a prediction. Okay, so here are the movies that I like out of this training set. So I liked Iron Man, I liked The Avengers, I did not like Clerks, and I really didn't like the Emoji Movie. So I've organized these. Yeah, right, nobody did. So the ones I like are on the top and the ones I dislike are on the bottom. So there's one really obvious potential rule you can see there. I'm sure everyone can see it. I like comic book movies. So if it's a movie about a comic book character, I'm more likely to like it. If it's not, I'm more likely to not like it. This rule is obviously insufficient because there's going to be a lot of movies that are not comic book movies that I liked. It's also insufficient because when we introduce a movie that's in the comic book category that I didn't like let's say Justice League, so that one I didn't like, but it's still a comic book movie. So now what do? How do we accommodate this? Well, I can just add another rule. So I can say, maybe I'm more likely to like it if it also got good reviews. So was it a comic book movie at the first branch, and then did it get good reviews? Well, in that case, I'll like it, and if not, I won't like it. So does this kind of make sense? So this process of building a tree, it's just called a decision tree, or a classification tree. And so the process is really simple. By the way, all this clip art is also movie clip art. So it's kind of a puzzle. Some of them will be obvious, some of them will not be. So in a classification tree, I want to first take my whole population and I pick the best rule that separates the population. So some rules might separate the population poorly, and some rules might separate them pretty well. So I pick the best one. And then once I've picked the best separator, I separate according to that rule, and now I have these two pools. Like, for example, back here, I had comic book movies and not comic book movies. And then I just repeat that process for each of my subgroups. And I can keep doing that over and over again. So that's called a classification tree, and it's one technique for learning an algorithm, for building a predictor. So here's another way of slicing it. So this is another predictor. So what movies do I like? I usually don't like period pieces. So I did like The Thing, but not King's Speech. But then, I actually really liked Hero. So maybe I like Chinese period pieces, but not non-Chinese period pieces. But then I don't think anybody liked The Great Wall, so I have to say, well, maybe if it doesn't have Matt Damon, then I like it. So this rule is obviously really complicated, right? And it probably won't apply to many other movies that I might see. How many other period piece Chinese movies with Matt Damon am I plausibly going to see in my life? Probably not many, hopefully not many. So there's two big problems with this kind of system. One is that it leads to very brittle rules that don't generalize. The other problem is that it's only giving me yes or no answers. It's not telling me how likely I am to like a movie. It's just saying yes or no. It would be really interesting for me to know there's a 51% chance I'm going to like this movie and a 99% chance I'm going to like another. Okay, so how can we solve those two problems? Well, there's a technique called random forest, and I want to spend a little bit of time on this just because I think it's a really interesting technique. So the way that a random forest works is that you start by taking a subset. You take many different subsets of your data. So you start by taking 50% of your data here, that's one pool, take another random 50% here, another random 50% here. And then you also, for those subsets, you forget some of the features. So in some cases, even though for every movie we know, yes, it's a comic book movie, yes, it's a period piece, you deny that information to the algorithm for some of these subpools. So basically, you're restricting the information that the algorithm can see in a lot of different subpools. And then on each of those subpools, you train a tree just like we did before. Now, these subtrees are each trained on less data, and they're trained with less information about that data than the decision tree that's trained over the whole set. So in some sense, they're each sort of impaired. They don't know as much. They all see different slices of the data. They see different features, but none of them knows as much as the overall data. So intuitively, you would expect that each of those trees is going to be less predictive than a tree trained on everything. And that does turn out to be true. Each individual tree is less predictive, but although it's hard to see because of the boundary there, in the end, what happens is that each of those trees votes to come up with the right answer. So now you build, let's say, 1,000 trees. Each tree is made from a subset of the data on a subset of the features. So each tree is individually less predictive, but then you take all 1,000 of them and you have them vote. And it turns out that that system is much more predictive and much better than building the decision tree. So here's an example of what that would look like with movies. So I build one tree where maybe you just get to see, is it a comic book movie, yes or no? Another tree, did it get good reviews or not? Another tree, is it a period piece? So I make a lot of these different trees, and then they all vote. So it turns out this fixes both problems that I described before. First of all, it's much more robust for data that it hasn't seen before, because principally it's because it hasn't had a chance to what we call overfit. So overfitting is when it builds the rule, like it's a period piece in China, not starring Matt Damon. That's a very specific rule and not likely to be correct in many circumstances, but the components of that rule can be correct more often than not. And so this fixes the robustness problem, and then it also has the advantage that it returns a probability. You can look at how many people voted, how many of your trees voted. If all 1,000 trees voted that you're going to like this movie, you can feel pretty confident that you're going to like it. Whereas if just more than half voted for the movie, then it's close. Okay, so the key thing here is that we are introducing deliberate diversity. We're basically creating, so this wouldn't work if we just trained 1,000 different trees on the same data set, because they'd all be exactly the same, right? They'd all have the same information, so they would all end up looking exactly the same. So we deliberately make them different by sampling the data and making it a smaller data set. And we create these imperfect copies of the data, and we create imperfect trees on that data, but yet they outperform a single perfect algorithm, which I think is really remarkable. This technique, a generalization of this technique, ensemble approaches, they're completely ubiquitous in modern machine learning. From a technical perspective, they reduce the variance in your predictions without increasing the bias. And here I'm using bias in a technical, statistical sense. Random forest, so I don't know how many people are familiar with Kaggle. Kaggle is a website where lots of people can go online and participate in machine learning competitions. And it's very widely trafficked. I don't know, hundreds of thousands, if not millions of people compete on Kaggle. And they have a really interesting data set of which algorithms are most predictive and are used most often in successful competitions or by successful competitors. Random forest is the third most popular technique on Kaggle. So let's go to the second most popular technique. This is called gradient boosting. So the idea behind gradient boosting, well, let me back up. With random forest, we made all those trees in parallel. None of the trees know about each other. Each one is independent. That's actually great from a scalability perspective, because if I have a big data center, I can have all of those trees training independently, simultaneously. It's what we call embarrassingly parallel. Gradient boosting is sequential instead of parallel. And the way gradient boosting works is that I take my data set, my whole data set and all my features, and I train one model on that. And then once I've done that, I look and see where the errors are. So I look at the mispredictions of that model, and now I train another predictor on the errors of the first predictor. And then once I see more errors from that, I train a third predictor on the errors from the second. And so you can see this sort of sequential process of building models on top of models. And so in the same way, you're introducing, they have the same data set but not the same features. So in the same way, you're introducing diversity in each of these steps. It's just happening in a sequential way rather than in a parallel way. Gradient boosting is the second most popular technique on Kaggle. And I guess actually what I'll say before moving on here is that people really didn't know if this would work until about 1990, I think was when the seminal paper on gradient boosting was written. Because the premise is that you take a collection of what are called weak learners. So each of these learners, they can all be different. They don't have to be the same. One can be a linear regression, one can be a random forest. Each of these learners can be very weak and have only, let's say, 51% accuracy. But when you collect them all together in the sequential boosting method, you can get what's called a strong learner, which is much more powerful than any of the individual ones. So again, what's happening here is that you're using the diversity of the individual weak learners in a very concrete way to build a strong learner that's much more predictive. Okay, so that's the second most popular algorithm on Kaggle. The first most popular algorithm, probably is not surprising to people, is a neural network. Deep learning, everyone's talking about it. It's a very successful technique right now. But what I want to point out with deep learning is that one of the most popular techniques that continues to be used in neural networks is a technique called dropout. So normally in a neural network, what happens is that you have inputs coming in here. Each of these connections represents a weight. They get sort of mushed together here and then mushed together here, and there might be multiple levels. And so the signal is feeding all the way through this neural network, and then when it gets to the end, you observe the errors, and then you do a process called backpropagation, where you adjust the errors. You take the errors and use them to adjust the weights just a little bit going all the way back. And you keep doing that backwards and forwards, and if you do that over a million images or a million samples of someone's voice, you can train a neural network to accurately identify images or voice or something else. But what dropout does is dropout says every time I put a new example in front of the neural network, I'm going to randomly take out half the nodes. So I'm going to randomly sort of impair this neural network. I'm going to make it half the size that it was originally, and I'm going to train on that one instance with that impaired neural network, essentially. And then when I have another instance, another piece of data, I'm going to drop out a different set of connections. So every time you're dropping out half the connections in this neural network. And to me, at least, it's not obvious that this would even work at all. I mean, you're throwing out half of the connections every single time you train a single instance. But it turns out this actually works better than a regular neural network. If you were to train it by keeping all the connections every time, this technique outperforms that in most cases. And the reason is that it allows you to approach essentially an ensemble of all of the constituent neural networks. So if you imagine there's n nodes in the middle, there's 2 to the n different ways, more or less, you could drop half of them, well, something like that, half of them out. It's exponential. So you're training an exponential ensemble of these neural networks in parallel. Each of them are themselves less efficient than the overall neural network, but because they observe different things and they see different features, the collection of all of those adds up to be, oops, I don't know what happened. Adds up to be very popular or successful. There we go. Okay. Yeah.
Does random dropout do better or worse than a sort of a combinatorial dropout where you don't replicate the dropout nodes? Do you know? Well, meaning if you're exploring a kind of quasi-ensemble, so each one is a kind of unique neural network, is it better to not replicate, sort of like...
Oh, just to train a whole bunch of neural networks?
Yes, that are effective dropouts without replicating the same dropout.
It probably would be, except that to train the exponential ensemble would be vastly more expensive. Yeah, so this is sort of, you can think of dropout as basically a highly efficient approximation of an ensemble of a bunch of different neural networks. So the running theme here is that an ensemble of less predictive individuals is going to outperform the best possible solo predictor. In this case, we're not using the sort of latent diversity, which is what I would say happens when you bring a bunch of different humans together. In this case, we're creating diversity by limiting what each individual in the network, which might be a neural network or it might be a classification tree, we're limiting what each individual can see and how it can learn. But the ensemble of all of those now diverse learners adds up to something that's much more powerful than what you would get by training it all at once. So in particular, we get 3 things. We get at least 3 things. We get better stability, which means that the predictions of our network or our model will vary less as we change some of the inputs in minor ways. We get robustness, which means that if we were to drop out parts of the network, it doesn't really matter. If we were to drop out constituent voters in our random forest, it wouldn't really matter because they're already sort of trained for that situation anyway. And most importantly, it gives us better generalization because we don't have those very specific brittle rules anymore. We have kind of more generalities in our network. So, and let me dig in just a little bit more to talk about why this happens. So let's imagine we're using something that's like height to predict what movies you're going to like. Unlikely that there would be much prediction, right, between height and what movies you like. And then let's also say our data set, let's say we didn't know that. We had no idea that height was a bad predictor, and in fact probably only noisy with respect to our target. Let's also imagine that we had two different measures of height, so feet and meters, and that they were both in our data set. And that happens way more than you would expect with the kind of data that people typically see in data science problems. So even a model as simple as ordinary least squares, if people are familiar with that, basic vanilla linear regression, what can often happen is that features will adapt. And so what that means is that the model might say, well, if I give a super high positive weight to the height in feet and a super big negative weight to the height in meters, those features both look really, really important to me. But what's really happening is they're just canceling each other out every single time, right? So if it's, if I give a weight of 3,000 to the height in feet and negative 1,000 to the height in meters, they're going to cancel out every single time. But that's a useless observation from the model's perspective. The model has co-adapted these two features in a way that's detrimental to its predictive power, because if you get a data set where those two things are slightly different, if there's a mismeasurement or conversion error, and now I see that the height in feet is a little bit different from the height in meters, which obviously shouldn't happen but happens all the time when you're using real systems, then suddenly that feature is super important and can really sort of drive you to wrong conclusions. So the way that many of these systems work is that they prevent specifically that co-adaptation of features, because in most of the constituent models, there's a high chance that both of those features won't be there together. So there will be many submodels here where there is feet but not meters, or vice versa, and since neither of them are predictive anyway, they won't show up. So that's one explanation for why this happens. There's others, but I just want to give you kind of a flavor of that. Okay, so summary for this part. Performance of a machine learning system is almost always improved by having a collection of diverse models rather than a single optimal model. And again, I think that's a very profound statement within the field of machine learning. And a different phrasing of that is this thing that people didn't even really fully understand until the 90s, which is that if you have a collection of so-called weak learners, all of which are slightly better than chance, but none of which are very good on their own, you can nonetheless pool them together in a specific way, in this case using boosting, so that you can create a strong learner that's way more powerful than any of the constituent parts. And that was, people didn't know that you could do that until gradient boosting was discovered. Okay, so that's the summary of the way that diversity plays into machine learning algorithms. I can pause here if people have questions, or we can take them at the end.
I had a quick question just about the voting mechanisms of these things. How is that organized, or is everything weighted equally in the voting?
So you could imagine, in a plain old sort of off-the-shelf random forest, it's completely equal. So you train all of these models completely independently. They don't even know about each other. They all have exactly one vote. You add up all the votes, and you're done. You could imagine, so in some sense, if you imagine a spectrum where that's on one end, gradient boosting is in some ways on the opposite end of that spectrum, because in gradient boosting, every model is specifically tuned to have the optimal weight based on what's gone before. So it's sort of a greedy selection of the optimal weights for a collection of learners. There's other ways to try and come up with that optimal selection of weights. A lot of them are very difficult. Gradient boosting is an efficient and effective way to do it, but it's not the only one. Yeah?
Are you, in essence, also combining the three different techniques to predict the same thing, or do you pick one technique over the other depending on the problem?
Well, that's a good question. Well, you'll find that practitioners often have favorite techniques. So if I've spent a lot of my time working with random forest, I get familiar with how to tune it and tweak it to make it work better on my problem. So that might be my go-to algorithm. Or if I'm a neural net researcher, I might feel really confident and comfortable with that, and so I might just decide I'm going to use that first for every problem. In a lot of cases, Kaggle is kind of an interesting, it's very useful to see which algorithms succeed on Kaggle, but it's also a little bit artificial in that people are typically competing for fractions of a percent. So for almost any of these problems, most of these learning algorithms will do about equally well. The one place where that's not true is on very high-dimensional data, images, voice, text, things where deep learning vastly outperforms these other techniques. But For kind of a medium-sized data science problem, mostly you'll find that random forest, gradient boosting, neural networks, they all work about the same, and it's kind of what you're most comfortable with. Yeah?
This will reveal how little I understand about data science, but would an even better one not be one that uses all three of those models?
Right. Yeah, so, and I think when we were talking about the Netflix prize yesterday, you know, the breakthrough with the Netflix prize was exactly this kind of ensembling, where you would have a lot of different models and you're completely agnostic. You know, I might have 8 different random forest models and a bunch of gradient boosting models. I'm just going to put them all together, and then I'm going to train something on top of that to combine them. So that's definitely common. It's more common, I would say, in some of these artificial scenarios where, you know, you're trying to eke out another 0.1%. It's less common in practice, I think. Yeah.
Let's see, so the random forest is a bit like wisdom of the crowds in a way, right?
Mm-hmm.
I mean, and I'm wondering, is there any formal work on, you know, proving a theorem about what it is? In other words, what it is you're optimizing, so that, which is the second question, could you have situations where you use this, and as in wisdom of the clouds, you end up in some other, you know, some irrelevant or misleading optimal solution?
Mm-hmm. So specifically with respect to gradient boosting, there is a good amount of theory around that, and that one has nice mathematical grounding, and people kind of understand why it works. I don't know the answer for random forest, whether or not there's good theory on that. If I had to guess, I would say there's probably not. It's probably just something that's empirically useful, and it works, and people, but I could be totally wrong. Yeah, yeah.
The question is there any other sort of other local minimum?
Yeah, I think
Or are there any examples of that?
there are definitely, so on the neural network side, there are cases where dropout does not work as well. And so, you know, there's not a whole lot of science usually. I mean, within certain problem domains, people now understand, okay, this works better than something else. But in many problem domains, there's not a whole lot of science as to whether dropout will do better or not. It often does, but not always. At a very high level, just the idea of ensembling multiple models that have some differences. So forget that even these kinds of differences. If you have a model that's trained with some kind of randomness, so that if you give it a different random seed, you'll get a different model, it's very common to let's just do 100 of those, average the results, and then we know that's going to reduce variance and not impact the bias. So that's a theoretically understood practice.
Are there well-understood conditions under which a collection of diverse models doesn't increase performance?
That's a good question. Well, I don't know is the short answer. I think that part of the reason is that it tends to be very hard to characterize what it means to generalize. That becomes a very complicated philosophical problem because you have to think about the problem space of other things that I might see sometime in the future and which of those things are reasonable from the perspective of evaluating my algorithm and which are not. So I'm sure you could construct artificial problems where an ensemble would fail to predict as well, but I don't know how realistic those are. But yeah, I don't know. Any other questions before I move to the next half? Okay, so now I want to switch gears. So we've talked about the ways that diversity at the algorithmic level can concretely make an algorithm better. But I want to talk instead now about this other sense of diversity. So we've been talking about we've been talking about algorithmic diversity and how it makes better predictions, but now I want to talk about once we have a prediction, how does it impact human diversity? And the emphasis here is not on the functional benefits that come from diversity, because that was really the first part of what I'm saying, and that's also part of what a bunch of the other speakers here have been talking about. But now we're in a situation, at least in this part of the talk, where we've got some kind of model and it's making predictions about some other population. And we don't necessarily understand how that population can be impacted functionally by our algorithm, but we can certainly understand how it can be impacted socially or ethically. And so now our concern is trying to understand the way that the algorithms that we're building now are impacting bias in some other group. Does that make sense? Okay, so our goal here is that typically we have some kind of ethical, social, justice, fairness related goal to reduce bias. And we want to do that, again, because we think it's ethical, not necessarily because we think it's functional. But before we can reduce the bias, we need to be able to measure it. So this is just one example. There's so many examples of bias in machine learning. I could give a whole talk on just those, and I don't want to do that. This is a case that was studied by Joy Buolamwini. She looked at a number of off-the-shelf facial recognition algorithms whose goal is to determine gender from an image. She acknowledges that even that is a little bit problematic because none of these systems have any acknowledgement of any kind of non-binary gender identity. It's all either male or female. But even with within the context of that setup, what she found is that those systems did really, really well for light-skinned men, but they did worse for every other category. So they did worse for light-skinned women. So you can see an error rate of 1% for light-skinned men and 7% for light-skinned women, lighter-skinned women. Meanwhile, I don't know if you can read that number up there, but 12% of darker-skinned males were misidentified, and then 35% of darker-skinned females were misidentified. So an error rate going from 1% to 35%, right? Again, this is one of 1,000 examples of bias in algorithms, and I want to come back to this example in a few minutes to try and decompose that and talk about why that's happening. Okay, but let's start with an easier example. We're going to go back to movies. So now we're going to try and, again, predict what movies I want to watch. So it's going to be the same system. We have something that's going to try and predict the probability that I'm going to like a movie, but we also have to introduce something else, which is how do I know what threshold to pick? So I'm probably going to watch something that I predict with 99% success, but what if it's 51%? Do I do that or not? So I want to talk about how we might make that decision. So I need a policy, basically. I need the predictor. That's the probability that I'm going to like the movie. It could be a random forest or a gradient boosting or a neural network like we just discussed. But it also could be just me pooling the opinions of my friends. I could ask people who know me and say, which movies do you think I'm going to like? It could just be me thinking about the movie, right? So the point I want to emphasize here is that now we're moving beyond just the world of the algorithm as implemented by machines. Now we're in the world of human policies as well. So these same arguments will apply equally to humans or to algorithms. So once I have a prediction about the probability, then I also need to pick a threshold. And so I can optimize for what we call recall, which is where I want to make sure that I don't miss a movie that I might end up liking, but I run the risk of also including some movies that I'm not going to like. Or I can optimize for precision, where I want to make sure that I only am watching movies that I like, but I'm also going to miss some other ones. And so we'll get a lot more into this shortly. So this is me just arranging along this x-axis, just the rough estimate of my own probability that I'm going to like this movie. So we already know I like comic book movies. I'm going to put those way down at the end. I love touring. Seems like, that's right up my alley. I'm going to put that way down at the end. I don't know much about Moonlight, but so since I don't know one way or the other, I'll put that in the middle. Blade Runner, I really want to like it, but I'm not sure, so I'm going to put that in the middle too. I hate period pieces, and that Hacksaw Ridge looks like an after-school special, so I'm not going to watch that. Shape of Water, I don't really know much about it. It's a love story. I don't like those movies, so I'm going to put that down there. Okay, so now I go and actually watch all of these movies. So I've arranged them along my scale, and now here's what happened. So Moonlight, I didn't know much about. I really liked it. As predicted, I liked both of those comic book movies. I was really disappointed by The Imitation Game. I thought I was going to love that movie and did not like it. Hacksaw Ridge met every expectation of not liking it. Shape of Water, I was surprised to find that I really enjoyed it. So this just represents, so again, the x-axis represents what I thought my probability of liking the movie was, and then whether it's above or below the line is what I actually decided once I watched it. So this is my probability prediction. Okay, but now let's talk about how I can pick a threshold, because once I've made a probability prediction, I still have to say, well, am I going to cut it off way towards the end and be really confident that every movie is going to be good but miss some, or am I going to cut it off way towards the other end and make sure I see everything but also waste my time on some movies that I don't like? So in this case, I've set the threshold, we can say this is, I don't know, like 70% here, and you can see down there, it's a little bit cut off, but the precision. So basically, of those 3 movies that I've seen now, I liked 2 of them. So my precision is 2 over 3, 67%. Of the movies that I actually ended up liking or would have ended up liking, there's 4 of those, and I only saw 2 of them, so my recall is 50%. right? So this is a trade-off. So I can move this down farther. I can move this threshold, and now when I move the threshold farther, now I have a precision of 60% because I liked 3 out of 5. And I have a recall of 75% because I saw 3 out of the 4 movies that were going to end up being good. But so this trade-off between precision and recall is basically just the way that I manage kind of the costs and the benefits of being right versus being wrong, false positives and false negatives. So the classifier in 2 steps is that I build this predictor and then I pick a threshold. I could have lots of other predictors. So a really dumb predictor would be the number of people on the poster, right? I wouldn't expect that to convey any useful information, and in fact, it doesn't, because if I make that, you can see that a lot of bad choices are right here near the front. So if I cut off here, I get worse precision and worse recall than I did in the first case. So that's so the point I'm making here is that the predictor itself plays a big role in this. Here's a slightly better predictor, historical period. I'm still going to miss some movies I would have liked, and I'm going to get a movie that I ended up not liking all that much, but I'm still going to get a pretty good coverage. If I had a perfect predictor, if I could actually simulate my own brain, then I wouldn't have any problems. I could get perfect precision and perfect recall immediately. Of course, we don't have that. Okay, so lots of systems can be thought of as exactly this kind of probability predictors. It can be a collective decision from a committee where I have 10 or 12 people and I ask them to vote. It can be an actuarial method like an APGAR score or something else where I have a system where I rate something on a few different factors and then I come up with a score. And it could just be my intuition. You know, if I'm interviewing a candidate and I don't have a formal process, I may just say I like that person, I don't like that person. It could be a machine learning algorithm like a random forest, neural network, ordinary least squares. These kinds of predictors and thresholds are used everywhere. So they're used for who gets a job. Even if you don't think that there's a process like that when you're interviewing someone for a job, that is the process. You have a mental model of someone's probability of succeeding in their job, and you have a threshold depending on how much you value a false positive or a false negative. It's used quite explicitly when people get loans. It's used when companies get investments. At venture firms, for example, it's very common in a venture firm to have a committee of investors who sit around a table and watch a pitch, and then people might vote. And so there's a certain threshold for which companies get investment then. It's used specifically for who gets parole, and I'm going to come back to that in a few more slides because that's a very important example. So let's do the same example, but now with loans. And so the reason I want to do this is because this is going to segue into the discussion about bias. But before I get there, this is basically the exact same example as before, except a lot more data points. So instead of movies, these are people who may or may not repay a loan. And so my slider here, again, is the probability that I think someone's going to repay a loan. So down here, I think these people are really unlikely to repay the loan. But look, some of them did, right? And over here, you know, I think these people are really, really likely to repay the loan, and some of them still didn't, right? And so my goal, so here this predictor is now fixed. This is something that's based on my observations of a population of people who have previously been given loans. I've done the best modeling I can do on this. This is now fixed and static. And now my job is to figure out where do I make that cutoff. So again, I need to trade off precision versus recall. So if I have a very high cutoff, you can see that I'm only going to get 14. I don't know if you can see that this is a little bit orange. I'm only going to get 14 people who paid their loans back in the end, and I'll get 2 who didn't. So if we say that it costs me $1 for every loan that doesn't get paid back, but I make $3 for every loan that does, I'm going to make $40 here. So I can just walk this line all the way down the x-axis, and see how much money I make at each point, right? And so if you do that, you'll find that it happens to be maximized at this threshold here. I think it's 66, if I'm remembering right. So here I'm making the most money I can make out of this system. And if I go all the way down to the end, I'm still going to do okay. I'm still going to make about $500, but I could make a lot more by putting my threshold up there at 67 or 66. So this is, again, precision versus recall. And in all of these examples, the best threshold is going to depend on the relative costs and benefits. So just a couple more examples of this. If I want to use the results of a blood test to decide whether I'm getting a second test, I almost always want that to be high recall, right? Because the cost of me taking a second test, I'm going to have some anxiety that maybe I do have this disease, whatever it is, and then I'm going to take a second test, which is probably relatively cheap. So I generally want to do that because the cost of not doing that might mean that I actually have a disease that goes undiagnosed or untreated. So that's a case where I want high recall. On the other hand, if we're talking about picking your next job, in this case, I actually want high precision because a false negative is pretty cheap. There's a lot of good jobs out there. If I miss out on one good job, there's probably another one that I'm going to also like. but it's pretty costly for me to take a job at a place that I end up not liking. So here I want high precision. Okay, so in summary for this part, what I generally want to do is I want to predict a probability that I should accept or reject, and then I want to pick a threshold based on my own costs of false positives versus negatives, and that's going to be application specific. Okay, so now we finally get to the point where we can talk about bias. So now we have two subpopulations, P1 and P2. So these subpopulations could be by gender, they could be by race or ethnicity, they could be by age, they could be by really anything. We assume that these populations have different distributions with respect to our predictor. If they didn't, then we wouldn't be able to distinguish between them anyway. So sort of by hypothesis, we have to assume they have different distributions. So how do we tell if our policy, which might be who gets a loan or who gets a job or who gets parole, how do we tell if our policy is treating those two populations differently? So let me back up and say, why would a predictor have different distributions for different populations? There's a ton of reasons. It could reflect a pre-existing bias. So if you consider the case, that we work in venture capital and we consider the case of investment. So why might different populations have different rates of investment? Well, in some cases, they might not even receive, let's say, seed funding before we see them. So there might be sort of a pre-filter. There could also be a post-filter. So if we fund a company, it may be the case that down the road it's harder for them to go public or to get acquired because of differences in population. So those represent pre-existing biases of the overall ecosystem. But it could also just be due to differences in the amount of data. So most humans and machines will make better predictions when they've seen more data. So if I see, well, actually I'll show you on the next slide, so I'll get to that. It could also be due to systemic problems with data collection. So the process of collecting data itself could be biased. So all of those, well, most of those actually come to play in this example, which I showed earlier. So I think it's a pretty safe assumption that these three different classifiers that were tested in this research paper were all trained on way more lighter-skinned males than on darker-skinned females, right? And so if your algorithm sees 1,000 lighter-skinned males and only 10 darker-skinned females, it's almost certain to be better at predicting lighter-skinned males simply because it sees more examples of them. There's also problems with systemic bias in data collection here because, as I learned from reading this paper, phone cameras are typically tuned to have better exposure for lighter-skinned people. So the pictures that you're getting that are fed into the system are the underlying data is biased in a way that the algorithm may not be able to account for. So there's many different ways that the different populations might be different when you run them through your predictor. Okay, so in this loan example, these are two subpopulations, P1 and P2. You can see that they look a little bit different, not a lot different. The main difference is that P2 has a smaller distribution of scores on the negative side. So these two populations, I'll tell you, these two populations have the same total size. They have the same success ratio, exactly 50% in both subpopulations succeeded. They have the same average score for successful loans, and they have the same average score for unsuccessful loans. So the sort of, the kind of first moments of these distributions are all the same. And so I think if I were to look at those facts, I might conclude that it's unlikely that my predictor would be biased in this case. Of course, I'm going to show you that it is. So if we pick a threshold based on max profit, 66 in this case, you can immediately see evidence of bias here because 64% of P1 receives loans and only 57% of P2 receives loans. So that's probably not an outcome that we want. And you can see why, because the sort of 66 or 67 threshold is about here. So what's happened is that the successful loans are about the same in both places. So if you use the same threshold here, you're going to get about the same number of successful loans, but you're going to not get some of the unsuccessful loans here. Whereas here, if you cut it off, you're going to get the same number of success, but you're also going to capture these ones that were unsuccessful. And so that's actually going to increase your raw count. So when we go back here, that's why in P2, we saw an investment in fewer total individuals from the pool. So that's probably not what we want. So one thing that you might try is, well, how about if we set the thresholds differently per population? Maybe that'll help. That actually makes it worse. So now I've raised the threshold even more for P2, so it's even harder for someone in P2 to get a loan. and a significantly fewer fraction of them receive loans. So almost twice as many people in P1 are now receiving loans versus P2. Okay, so that's probably not what we want. So the next thing we can try to do is what's called demographic parity. We can try and optimize so that the same percentage of people in both populations receive loans. We still have different thresholds. It's still harder for someone in P2 to get a loan because the threshold is higher. And maybe more importantly, if you now look at the percentage of people who were successful, and by successful I mean people who went on to repay their loans, so the good actors in the situation, many more people in P1 who went on to be successful receive loans versus P2. So again, that doesn't seem very fair. So you can try one more thing, which is to optimize for the same success percentage, which is called equal opportunity. Now here what's happened is that we've pushed the problem in the other way. So now we have 98% of the successful people receiving loans, which is good, that's equal. But now it's actually, we see a larger percentage of people in P2 getting loans, which might be okay. Maybe we think that's the right social outcome, but there's a clear difference here. And the other thing to note is that we've had to turn our success percentage all the way up to like 98%. So almost everybody's getting a loan, 99% in P2 and 83% in P1. So our profit is going to be down a lot. So we may not be a profit maximizing organization. We may decide that's perfectly okay. But it's a fact that if we adjust these thresholds in this way, we're also not optimizing for the outcome. So the analogy here is that as you're trying to push one thing up, the other thing goes down, and vice versa. You're sort of pushing things around, but you're never actually getting everything to align perfectly. And in fact, people didn't really understand this problem. This gets shown in a lot of this gets shown in a lot of conferences on fairness and ML. It's not mine. People have started to realize now that this is a fundamental problem. And so starting in 2016 and 2017, you started to see a lot of good work done on this. And now there's a ton of research on this problem. And the main takeaway is that it's actually impossible to be completely fair in this situation, which to me was a surprise. So under reasonable assumptions, you cannot simultaneously optimize your overall accuracy or profit, the best or optimal accuracy or profit across different subpopulations, equal treatment, which is the same threshold across two subpopulations, equal acceptance rates or demographic parity, which means the percentage of people who receive loans in the loan case, and then equal success rates, so equal opportunity, so the percent of people who are going on to repay the loan, that can't be equal. So you can make one of them equal, and maybe if you're lucky you can get two of them to be equal, but you really can't make all of those things equal at once, which is disappointing. So the fundamental reason for this impossibility is basically imperfections in the classifier. If we had a perfect classifier that could predict everything perfectly and that had no error rates, then of course we could achieve whatever success rates we wanted. But no classifier is perfect, and in particular, in most cases, our data set itself is imperfect. And what I mean by that is that in our data set, there will be people who are essentially the same on a bunch of attributes, on all the attributes in the data set, but have different outcomes. Because you can imagine, if you're predicting someone's loan repayment based on their credit score, there's a lot of people who have a credit score of 652. And so some of those people will repay and some won't. But you can never perfectly predict those outcomes based on the data set because you don't have enough other predictors in the data set. There's not enough things that you can observe to make a perfect prediction. So it's really intrinsic to the classifier. Okay, here's a bunch of references, and I really recommend the first one. Maybe we can email out the link or something, but all of that previous discussion of loans is directly based on this interactive sort of experiment from Google Research called Attacking Discrimination in ML, and they have a bunch of nice sliders where you can move. They have similar populations, and you can move the sliders around and just sort of see for yourself that it's impossible to make all of them line up perfectly. But then this paper on attacking discrimination with smarter machine learning is the more technical work on this. Okay, so I want to now talk about a case study because I think we can all imagine how these decisions can have very serious real-world impacts. So some of you may have read about this. There's an algorithm called Compass. It's a tool created by a company called Northpoint, and it assigns a likelihood that a defendant will reoffend. It's based on 137 factors. There's a bunch of personality tests, things like, has anyone in your family gone to jail? Have you ever felt angry. I mean, there's a lot of different sort of psychometric tests that they give, or questions that they ask. Race is not one of the inputs to COMPAS, but of course it's correlated with some of the other predictors. It's used in a bunch of states, and in particular, for example, in Wisconsin, this is a quote from a Washington Post article on this. It's used at each step in the prison system from sentencing all the way to parole. So this system is exerting tremendous power over hundreds of thousands of people. Northpoint claims that their tool is unbiased because race is not an input to the tool. Okay, so ProPublica did a study, and they found that among defendants who did not reoffend, so remember this is that equal opportunity metric, which was the last one we talked about. Among defendants who did not reoffend, blacks were more than twice as likely as whites to be classified as medium or high risk. So obviously erroneously classified because none of these people reoffended. So this clearly violates this equal opportunity metric that we were talking about. And I just threw in a quote from Eric Holder, which was not specifically about this controversy, but is the general concern. Although these measures were crafted with the best of intentions, I'm concerned that they inadvertently undermine our efforts to ensure individualized and equal justice. Okay, so there's clear bias in Northpoint's tool, and then the question is, are they just naive, right? Maybe, and when I heard about this, my initial perspective was, well, you know, I mean, you can give anybody a machine learning tool off the shelf and they can have an opportunity to misuse it and they won't think through the opportunities for correlation and bias. But that turns out actually, the truth turned out to be more subtle. So Northpoint's response is that within each risk category, the proportion of defendants who reoffend is approximately the same regardless of race. So Northpoint was actually trying to optimize a different criterion for bias. They were trying to optimize demographic parity as opposed to this equal opportunity metric. Northpoint claims in this debate that their definition of fairness is actually better than ProPublica's, right? So now we have two different definitions of bias, and the key thing is that it's mathematically impossible for any algorithm to simultaneously satisfy both of those definitions of fairness at once. So we can either go with Northpoint's definition of bias, or we can go with ProPublica's. We can't have them both.
So conditional probability in Northpoint and just frequentist in ProPublica.
I guess I think of it in the denominator. So the numerator in both cases is who was predicted not to reoffend and didn't reoffend.
Yeah.
And in Northpoint's case, it's this, the denominator is basically everyone in a particular population. And in ProPublica's case, it's everyone who truly didn't reoffend, whether they were predicted to or not.
Okay.
So, and really these are, you know, not precisely, but conceptually this is like the precision recall trade-off from before. And so for the same reasons, you just can't have both of them optimized at the same time. And the root problem, again, as I mentioned earlier, is that the data is just not perfectly predictive. We don't have good enough data about human beings to predict whether they're going to reoffend. All we can do is assign these probabilities, and that's how we get into problems. So I'm almost done. What should we do about this? Well, one thing we could do is we could agree on the type of bias that we want to reduce, possibly at the expense of other kinds of bias. So we could decide we care about equal opportunity or we care about demographic parity. But if we care about one, we have to not care as much about the other. And then there's the following question, which is who gets to decide? I think most of us would probably agree that it's not a private company like Northpoint, even if their intentions were good. It should probably be a discussion amongst citizens. The other alternative is you can just change the whole system. So this was mentioned in the Washington Post article. Maybe we shouldn't use risk scores to determine who has to pay bail, because bail as a concept is just a bad one. And so maybe it's actually better if we just uproot the whole system. That might be possible in this case. It might not be possible in other cases to take such a dramatic approach. Okay, so summary. Fairness across multiple metrics is usually impossible. There are a few very special cases where it's possible, but in almost all cases it's impossible to optimize all of these fairness metrics at once. It's not enough to just measure bias on one of these metrics or even correct it in a single metric, because that's probably going to raise bias in other cases. So before we can even start to think about an algorithmic solution, we really have to fully understand what our priorities are in each particular case. So in parole, we have to understand what is it that we want to optimize? What do we think is the most fair approach, the most just approach? And then we can figure out an algorithm that satisfies that, or we can tune an algorithm that we already have. But we can't go into the problem without addressing that first. So that's it. Thank you. Any questions?